Earth has survived asteroid impacts, supervolcanoes, and mass extinctions that erased almost all life. But the greatest threat to our planet is still ahead. It won't come from space. It won't come from within Earth. It will come from the very star that gave us life. Earth feels permanent, solid, unchanging. Mountains seem eternal. Oceans feel endless. The ground beneath our feet appears immovable. But in reality, our planet is anything but stable. If we could fast forward time, even slightly, Earth would begin to feel unfamiliar. And if we push that timeline far enough, millions, then hundreds of millions of years, the world we know dissolves entirely. Not because of an asteroid, not because of nuclear war, but because Earth itself never stops evolving. Let's begin by removing ourselves from the equation. No humans, no technology, no interference. What follows is Earth's natural future guided by physics, geology, chemistry, and time. A billion years may sound abstract, but consider this. 1 billion years ago, plants had not yet colonized land. Oxygen was scarce. The continents were fused into a single colossal landmass. Earth was already ancient and yet completely alien. The future will be no different. One of the most powerful forces shaping the future lies beneath our feet. Plate tectonics. Earth's crust is broken into massive slabs that drift slowly atop the semi-molten mantle below. These tectonic plates move at roughly the speed our fingernails grow, almost imperceptible in a human lifetime but unstoppable across geological time. Over the next 100 million years, the continents continue their slow migration. Africa begins tearing itself apart, forming new ocean basins before slamming northward into Europe and Arabia. The Mediterranean Sea is squeezed shut, replaced by a colossal mountain chain stretching from modern Spain to western Asia, possibly taller than Everest itself. Australia drifts north, colliding with Southeast Asia. Entire island chains are crushed upward into new mountain systems. Meanwhile, the Atlantic Ocean widens as North America and Eurasia pull farther apart. California begins its long journey north, eventually fusing with Alaska and creating an entirely new mountain range along the western edge of North America. Nothing on Earth's surface is fixed. Continents are reshaped, erased, and reborn, but this is only the beginning. Around 250 million years from now, the continents converge once more, assembling into a new supercontinent often referred to as Pangaea Proxima. The Atlantic and Indian Oceans close. Vast inland seas form, cut off from global circulation. This rearrangement of land and water triggers catastrophe. Ocean currents are responsible for distributing heat and oxygen begin to collapse. Without circulation, deep ocean waters lose their oxygen entirely. Marine ecosystems suffocate. Entire food chains unravel. Another mass extinction sweeps the seas. On land, the situation is no better. Far from the coasts, massive continental interiors bake under extreme heat. With little rainfall and violent seasonal temperature swings, vast regions become deserts. Daytime temperatures soar beyond 50 degrees Celsius. Only narrow bands near the poles remain even remotely habitable for complex life. Yet even this supercontinent is temporary. Over tens of millions of years, Earth's crust fractures once again. The continents slowly drift apart, continuing a cycle that has repeated for billions of years. Mountains erode. New oceans form. Old ones vanish. To us, these changes would feel apocalyptic. To Earth, they are routine, and despite how dramatic these surface transformations appear, they pale in comparison to what's coming next, because the greatest threat to life on Earth isn't shifting continents or collapsing oceans. It's the sky above us. For billions of years, the sun has been Earth's greatest ally. It warmed our oceans, powered weather systems, and fueled the chemistry of life itself. But stars are not static. They age, they evolve. And slowly, almost imperceptibly, our sun is changing. Right now, deep within its core, hydrogen atoms are being fused into helium. This process releases enormous amounts of energy, which pushes outward, perfectly balanced against the crushing pull of gravity. For a long time, this balance has kept the sun stable, but helium is heavier than hydrogen. As hundreds of millions of years pass, helium ash builds up in the sun's core. The core becomes denser, tighter, and hotter. Fusion accelerates. And with it, the sun's energy output increases. This isn't a sudden flare or violent explosion. It's a quiet betrayal. Every 100 million years, the sun grows about 1% brighter. That doesn't sound like much, but Earth's climate has always depended on razor-thin margins. Life exists here because temperature, chemistry, and atmosphere sit in a delicate balance. 500 million years from now, the sun will shine roughly 5% brighter than it does today. The consequences ripple outward across the planet. Higher temperatures speed up chemical reactions everywhere, especially on land. Rainwater absorbs carbon dioxide from the air, forming weak carbonic acid. When this rain falls, it weathers rocks faster and faster, pulling carbon out of the atmosphere and locking it into minerals that wash into the oceans. This process has always acted like a planetary thermostat. But now it runs too efficiently. Volcanoes can no longer replace carbon dioxide as quickly as it's being removed. Atmospheric CO levels begin to fall in life. Notices immediately, plants are the first to suffer. Photosynthesis depends on carbon dioxide. Without enough of it, plants can't produce more energy than they consume just to stay alive. Growth slows. Forests thin. Grasslands retreat. Most plants on Earth today use a method known as C3 photosynthesis. It's effective but inefficient. As carbon dioxide drops below critical levels, these plants begin crossing a dangerous threshold. They are no longer growing. They are merely surviving. Then, one by one, they disappear. Forests don't burn. They don't collapse overnight. They simply fail to regenerate. Entire ecosystems unravel silently. A small group of plants known as C4 plants manage to hold on. Their specialized chemistry allows them to survive on much lower CO levels. For hundreds of millions of years, they become Earth's final green survivors, clinging to life under an increasingly hostile sun, but even they are only buying time. As plants vanish, oxygen production collapses. The air grows thinner, poorer. Herbivores starve first. Carnivores soon follow. Complex life doesn't suffocate, it runs out of food. By the time the sun reaches 10% greater brightness, roughly 1 billion years from now, Earth has crossed a point of no return. Average global temperatures surge past levels mammals can tolerate. Vast regions exceed 50 degrees Celsius. Rainfall becomes erratic. Deserts spread across once fertile continents. The planet is still alive, but only barely. And while the land struggles, the oceans face a slower, more terrifying fate. As temperatures rise, evaporation accelerates. More water vapor enters the atmosphere, trapping heat even more efficiently. A powerful feedback loop begins to form. The sky itself becomes a greenhouse. At first, the water cycle continues. Rain still falls. Rivers still flow. But the balance is slipping. Each year, more water escapes into the upper atmosphere. Where solar radiation tears it apart, hydrogen drifting into space. Lost forever, Earth is bleeding its oceans into the void. We've seen this story before. Next door, Venus stands as a warning, once possibly Earth-like, now a furnace hot enough to melt lead. As our planet heats up, the similarities become harder to ignore. The question is no longer if Earth will change beyond recognition. It's how much longer life can endure before the sun finishes what it unknowingly started. For most of Earth's history, water has been life's greatest shield. It softened temperature extremes, moved heat around the planet, and gave biology a place to begin. But under an aging sun, even the oceans are not safe. As the planet continues to warm, evaporation intensifies. Vast amounts of water rise into the atmosphere, thickening it with water vapor, a powerful greenhouse gas. Each degree of warming allows the air to hold even more moisture, trapping additional heat and accelerating the process. At first, the change feels gradual. Clouds grow heavier. Storms become more violent. Rain still falls, rivers still flow, and the planet appears stable, but this stability is an illusion, high above the surface. In the upper atmosphere, solar radiation splits water molecules apart. Oxygen lingers. Hydrogen escapes into space, light enough to slip free of Earth's gravity. Every escaping atom is a permanent loss. The oceans are no longer circulating, they are leaking over millions of years. This slow drain becomes irreversible. The balance tips and Earth enters a runaway greenhouse state. Water vapor accumulates faster than it can be removed. Temperatures surge. Evaporation accelerates even further. The sky becomes thick, hazy, and suffocating. Earth is now walking the same path as Venus. As the seas retreat, coastlines shift inward. Shallow oceans vanish first, exposing vast salt flats where marine ecosystems once thrived. Coral reefs bleach and crumble. Phytoplankton, the foundation of oceanic food webs, collapse, removing the last significant source of oxygen from the planet. By this stage, roughly 1 billion years into the future, more than a quarter of Earth's original ocean water has already been pulled deep into the mantle through subduction. What remains at the surface is disappearing into the sky, yet Earth is not completely dry, not yet. Deep beneath the crust, locked within minerals and the mantle itself, lies enormous quantities of water, possibly several times more than all modern oceans combined. Over geological time, some of this water seeps upward through volcanic activity, briefly replenishing the surface, but it is no longer enough. With rainfall dwindling and rivers fading, the final refuges of surface water retreat toward the poles. Shallow polar lakes form in the coldest regions of the planet, isolated, nutrient-poor, and lifeless. No plants remain to feed them. No ecosystems survive to depend on them. Eventually, even these last puddles evaporate. Earth becomes a desert world. Vast fields stretch across the equator. Ancient seabeds transform into blinding salt plains. The sky glows with trapped heat beneath a dense, atmospheric blanket of carbon dioxide and water vapor, and something else begins to fail without surface water. Earth's crust dries and stiffens. Subduction, the process that recycles crust back into the mantle, slows, then stops entirely. Plate tectonics grind to a halt. The planet's surface freezes into a rigid shell. Without this geological engine, volcanoes become rare and localized, erupting only over deep mantle hotspots. Over time, these volcanoes release trapped carbon dioxide into the atmosphere with no efficient way to remove it. The planet grows even hotter. By now, no plants remain. No animals. No forests. No oceans. Only life at the very edge of survivability persists, deep underground. Within shaded rock fractures and ice-filled caves, extremophile microbes cling on. Some survive in salty brines. Others endure crushing heat and near-total dehydration. A few may even drift high into the atmosphere, floating in cooler layers far above the scorched surface, echoing theories about possible microbial life in Venus's clouds. These are Earth's final inhabitants. They endure for hundreds of millions of years, outlasting oceans, forests, and entire biospheres. But even they cannot survive forever. As the sun continues to brighten, surface temperatures climb beyond 150 degrees Celsius. Even the poles bake. Underground refuges dry out. Atmospheric niches collapse one by one. Earth's last microbes perish. The planet falls silent. If an advanced alien civilization were to pass by Earth 3 billion years from now, their instruments would detect nothing unusual. No oxygen imbalance. No organic signatures. No hint that life ever existed here. They would see a barren, rock-scarred, overheated, and lifeless, never knowing it once hosted oceans, forests, and thinking beings who wondered about their place in the cosmos. But Earth's story does not end here, because while the planet dies, the sun has its own destiny still unfolding. For billions of years, the sun has been the quiet engine of the solar system, a steady light, a constant presence. But stars, like all things in the universe, are mortal. Deep within the sun's core, hydrogen is slowly running out. When fusion can no longer continue at the center, the delicate balance between outward pressure and gravity collapses. The core contracts, growing hotter and denser by the second. In response, hydrogen fusion ignites in a shell surrounding the core, releasing a torrent of energy. The sun begins to swell. Over the next billion years, our once stable star transforms into a red giant. Its outer layers expand outward, growing hundreds of times larger than their original size. The sun's surface cools and reddens, but its total energy output explodes, becoming hundreds, then thousands of times more powerful than today. From a distance, the solar system becomes unrecognizable. As the sun loses mass through intense stellar winds, its gravitational grip weakens. The outer planets drift outward, their orbits expanding into the darkness. Jupiter and Saturn retreat. Neptune slips even farther into the cold. Earth's orbit also moves outward, at first. For a moment, it seems like our planet might escape, but tides tell a different story as the red giant grows. Powerful tidal forces begin draining energy from Earth's orbit, pulling it slowly inward. The expanded sun now looms enormous in the sky, filling half of it, its churning surface glowing like molten fire. Around 7.5 billion years from now, the sun reaches its maximum size over 250 times. Its current radius, Earth crosses the point of no return. The planet plunges into the sun's outer atmosphere. Any remaining crust vaporizes instantly. Mountains, plains, and ancient seabeds dissolve into plasma. The last atoms of Earth are stripped away and mixed into the sun's bloated envelope. Our planet doesn't explode. It simply ceases to exist for a brief time. Earth becomes indistinguishable from the star that once gave it life. Then, just as dramatically, the sun's fury fades after shedding vast amounts of mass. The red giant collapses inward. Its outer layers drift away into space, forming a glowing planetary nebula, an expanding shell of gas enriched with elements forged over billions of years. The center remains the sun's exposed core, a white dwarf. No larger than Earth once was, yet containing half the sun's original mass. This stellar ember shines fiercely at first, but without fuel it slowly cools, fading over trillions of years into darkness. The solar system is gone, the inner planets are ashes. The outer worlds wander silently in widened orbits around a dead star. Any trace of Earth, its oceans, forests, and civilizations has been erased, and yet, this is not a tragedy. Every atom that once formed our planet was forged in ancient stars. Every element in our bodies was created in cosmic furnaces long before the sun was born. In death, the sun returns enriched material back to the galaxy, material that may one day form new stars, new planets, and perhaps new life. Even if Earth's story ends, the universe continues. And so does ours, if not in form, then in legacy, because the cosmos does not waste its creations. It recycles them.